In this lesson, we will discuss mining diverse patterns. We will go over mining negative correlations and mining compressed and redundancy-aware patterns. Negative patterns are item combinations that are unlikely to happen together. These patterns are useful to identify mutually exclusive preferences. For example, a customer is unlikely to buy a Ford Expedition SUV and a Ford Fusion Hybrid at the same time. This is not impossible. Maybe a family will come and make this purchase, but still this is a negatively correlated pattern. Now, how to define negative patterns? A simple support-based definition is given by support of A and B much less than the product of support A and support B, which directly relates to the notion of the left, which is the ratio of support A and B over the product of support A and B. In this example, we show how the number of transactions can alter the outcome of negative correlated patterns. Suppose a dealership sells vehicles type A and type B, sold 100 each, but there is one transaction that contained both A and B. Plugging the numbers, support A and B is 1 over 200, support A 100 over 200, support B 100 over 200. 0.005 much less than 0.25, which concludes that this is a negatively correlated pattern. Now let's go and exaggerate the number of transactions. We have sold 10 to the power 5 cars, so the support is very, very small, but then the product of support A and support B, when you multiply the values, is just going to be even much smaller. So we're going to falsely conclude that this is not a negatively correlated pattern. Actually, it's a strong positive correlation, whereas the null transactions affected the outcome of this simple definition. To avoid the effect of null transactions, we pick a null-invariant measure like Kulczynski, which finds the average of support A and B over support of A and support A and B over support of B. This quantity needs to be less than epsilon, which is the negative pattern threshold. Now we plug in the values from the previous example, and we show that under the Kulczynski measure, it remained a negative correlated pattern. So in summary, Kulczynski is invariant to large number of uncorrelated transactions, and it better captures how rare is the co-occurrence of patterns. Moving to mining compressed patterns, let's start with some motivation. So when we run pattern mining algorithms in class or homework, we usually work with small datasets. But in practice, these algorithms are applied to very large datasets. For example, imagine analyzing all the transactions at Amazon.com for the last 20 years or so. And businesses for sure interested in finding out what patterns to be discovered. But the key issue, there will be large number of patterns with high support to be mined, and we need to know how to report these patterns. If you take a look at this table, we have 5 patterns. Pattern 1 and pattern 2 almost identical with the exception of 17, and they have somewhat very close support. Do we need to report both patterns, or how do we deal with that? Next, we are going to discuss a few solutions. One solution is to look at closed patterns. For example, P1 is closed. If you add item 17, the support will drop. So closed patterns preserve support information while avoiding redundancy. Another option is to use maximal patterns. For example, P3 is a maximal pattern because it contains the others. However, using maximal patterns can cause information loss. If we look at the support alone, P1 and P2 both have support around the 205K, P4 and P5 around 161K, and P3 is on the lower side, but this is the maximal pattern among those. This table and these numbers suggest that there is natural blocks of patterns with similar support, but closed and maximal patterns don't always capture this blockedness structure. So we need more methods to explore. The next measure is distance-based measure. Intuitively, we can define a pattern distance measure. For two patterns P1 and P2, let T of P denote the set of transactions containing P, so the distance becomes 1 minus the number of transactions that contains both P1 and P2 over the total number of transactions. In this example, the distance between P1 and P2 is 1 over 5, which is small, which means these patterns are somewhat similar. We can also use the distance in clustering patterns. We can apply delta clustering, which means group together all patterns whose distance is within some threshold, which is the delta, and then choose a representative pattern for each cluster. In summary, distance-based clustering provides a good balance. It compresses the pattern set while preserving meaningful differences. Finally, redundancy-aware top K patterns starts with embedding patterns with some color coding in the two-dimensional space. Then runs a variation of the top K algorithm to identify important patterns. Starting with figure A, each dot represents a pattern. The grayscale shading indicates support. Darker dots correspond to higher support. Now moving to figure B, if we use the traditional top K approach, we simply select K patterns with the highest support. For example, K equals 3, we just take the 3 darkest points, but the problem that these patterns are often very similar to each other, so we essentially report multiple variants of the same frequent patterns. In figure C, summarization or clustering ignores support completely and instead uses clustering. Here we pick one representative from each cluster, which ensures diversity among patterns, but this approach may discard patterns that actually of high support. Finally, a redundancy top K approach, it tries to balance patterns significance while lowering redundancy. In other words, the redundancy-aware top K method, it tries to produce a small set of patterns that are both informative with high support and diverse, which means lower redundancy. In summary, we discussed mining diverse patterns.